Well, dear, welcome back. And you have started watching video on artificial neural network. And today we are going to discuss a very important algorithm in machine learning, which is known as back propagation algorithm. Okay, so in that context, in my earlier lecture, I just talked about a neural network having hidden layer. So these are called hidden layer. Why they are called hidden layer, because they hide the desired output in this layer. Okay, so this is an example of fully connected layer. Okay, so I need to now formulate a training algorithm, right? So uh, in a fully connected layer means that output of a particular neuron in a particular layer is connected with as an input to all other neuron in the next layer. Okay, so this is the meaning of fully connected neural network. Okay. Now let us try to understand how the algorithm can be formulated. So as you know, I have data set X and Y. Okay. So Y desired corresponding to some X as input. I have desired Y where at the output layer. And whimsically I have selected Wij, Wjk and all the parameters, network parameters, right? Including bias. So the notations now let us in a generalized way try to understand that we are considering ith input. Okay, then we are considering jth neuron in the hidden layer. Total number of neuron are m, and we are considering another neuron k in the output layer where total number of neurons are l. Okay, so as you know that here we cannot now we can calculate error here, but we cannot use the error as a raw material to compensate the W parameters like the way we did in simple delta learning rule of perceptron, right? Why? Because, for example, the error here is contributed by so many different uh, um, outputs from the previous layer, and unless I know who has contributed how much, then I cannot compensate whimsically or equally to them because my algorithm will not run efficiently in that case. So what I need to do is I need to calculate error gradient. Error gradient. Okay, so why you need to calculate error gradient? Because I have a network now, and I need to compensate. I need to use error to compensate the parameter, right? And to actually tune the parameter. A good way of telling is tuning the parameter. Okay, and for how to calculate error gradient? Error gradient means I'll have to have a activation function which is differentiable. That's why kind of hard limit function will not work here the way it worked in perceptron. Why? Because this has discontinuity here and here. Okay, I need a continuous curve. So sigmoid is good choice for that. Okay, sigmoid, tan sigmoid, and many more such ReLU, for example, rectified linear unit, and all kind of things. Whichever function has good range and continuity have been tried. And here actually we are giving you with the example of sigmoid function. So this is basically exactly now this neuron is nothing but your logistic regression unit, which you have already studied. Okay, and I can differentiate this. And one good thing about this differentiation, I have already done it earlier. You can do it. Okay, that it can be expressed in terms of the output. You see how? So let us consider now specifically. So this is my um, function gx equal to 1 by 1 plus e to the power minus x. Okay. So I am now considering kth neuron at a particular epoch p. So now my notation will be xk particular epoch p. I am differentiating that function with respect to the xk, okay, and that turns out to be, just you do it by assuming this as z, differentiate this, you will get this e to the power minus z uh, um, divided by 1 plus e to the power minus z square, right? This is u and v. You can just differentiate this function. And just a little bit trick I have used here. So this has been taken aside here, and instead of this we have written this. Why? Because I need to make the calculation very easy. And now if I put YKP, that is input at a particular epoch P for this neuron K, this is my input, which is incidentally the output. That's why we are writing Y also, output of these neurons, right? But for this neuron, these are the input. Okay, I am putting this instead of 1 by 1 plus is 1 minus J. So differentiating this function will yield YKP times 1 minus Y sub K P. This you have already seen in logistic regression, so it's a repetition, right? So anyway, now error gradient will be rate of change of input with respect to the parameter times the total error. Means this error, total error, has been contributed, which has been obtained by differentiating the activation function with respect to the parameter, right? And we have ended up with this. This is very, very important issue, right? Now let us try to, as earlier, weight correction now can be done, because weight correction in the JK, WJK. So we are considering this neuron. Okay, this one. Okay, so WJK, delta WJK equals to, as usual, alpha is learning rate, say 0.01. Okay, now Yj, where Yj is actually, Yj is the output of this neuron, output of this neuron. Okay, so output of this neuron and input to this neuron. Okay, so I am able to calculate the error gradient for this now. And the thing is, now since it is error gradient, I can use it for instead of error. So earlier in perceptron, this was clearly the error which we multiplied. Okay, here we have error gradient and we need to multiply, because this is representing the error for this particular input, which is associated with this weight. This is intuitively is very important to understand, because this error here is contributed by these so many inputs here. Okay, Y, J, right? So those inputs times error gradient has to be used as a raw material for compensating delta W. Okay, so now instead of this, I can use that deduction, this times this. Okay, Y sub K for a particular epoch P. We can ignore this, it is already written. It's a P is for particular epoch. Okay, 1 minus Y sub K P times error K for that epoch. So I have error only here. Okay, but now I am able to calculate that effect of error in the form of error gradient and incorporate that error in actually compensating my delta JK. And once this parameter is there, then you can upgrade JK equals to W JK plus delta W JK, like this. So new assignment of JK will be earlier JK plus delta W, right? So this is delta learning rule, and this is similar. So in disguise, this is nothing but your gradient descent algorithm. If you just remember, okay, this you got also in differentiating that function jw with respect to wj. eh? You remember, for one sample you had minus yi, right? And then for one sample, this was times xj, okay? Because this was equals to w transpose xj. So you remember this, right? So that's why this xj is coming. So similar, you see, this is input xj. This is analogous to this, okay? And this, what is this? This is actually error, okay? Error p, say in this particular case k, and this is just I wanted to draw analogy so that you will be able to digest properly what is happening. Okay. Okay. So far so good. So I have I have error at the output layer, and I have used that error as a raw material for output layer weight correction. So all the output layers, this all the weight correction WJK can be done. Okay. So now we'll have to another challenge. We have another challenge. We have to calculate Wij. This parameter error correction has to be done, and using the same error. Okay. So how this thing can be done? So weight correction in the hidden layer. How it can be done? You see, same thing. Alpha xi for a particular epoch p. So this should be actually, if I am missing, don't worry about this. Okay. So this is the weight correction, alpha learning rate as usual. Then input times error, but here error is uh, denoted by error gradient. Similar, right? So here also the output of this has contributed some error, isn't it? Because this W at the beginning of the algorithm, W are not perfect, right? So they are actually contributing error. Only difference is I do not know, I cannot calculate the error here. I can calculate only error here, but error will be there. And that error gradient is delta JP. Okay. And now my challenge is to that in a chain system, I will have to come that from here to here and from here to here. Okay. So because this error already known to me, so that's why you see the way we are doing it. Actually, this has been contributed um, for kth neuron. This time multiplied by delta kp times wjk jk p for a particular epoch k equal to 1 to n. Okay, so every um, this error gradient is contributed, of this error has been contributed by these all these neurons. Plus this error is actually a continuation of what these also contributed here. So this error contributed by this by error gradient, right? And as those accumulated error contributed, those error are contributed by this neuron as this input. So it is propagated here. So in this form, I'll have to. So this is very important to know that this additional term will be coming, because I think intuitively you can understand, right? That this is the hidden layer. I know the error gradient of the hidden layer. So yj, okay, into 1 minus yjp, these are my this layers say input, which is the output of this non-computational, in this particular case, layer, right? So that I can know that this times this also has been propagated, right? So error contributed here, this and the error from here. So this is what the error correction has to be made in the hidden layer. So intuitively, this is the mechanism with which the error is actually propagating from layer to layer to layer, and that error propagation actually is giving you weight compensation. And in the algorithmic way, you'll have to train. That means network training means you have level data for this x, you know this y. For another set of x, another set of y. Another set of x, another set of y. You know. And from there, you just try to run the algorithm, which will compensate all the parameters in the output layers, start from output layer. After compensating, it will start here, and then compensate all the parameters in the hidden layer. Okay, so and this way, if more hidden layers are there, same thing is to be repeated for because error is only known here, and we need to propagate one after another, till. Okay, so this is the back propagation algorithm. So to digest this, we need to take one problem. Say in the next class we'll do by hand. We'll try to solve the unsolved problem of XOR. That is X1 two input XOR, right? So this is the training data set which we usually use. Okay, so this is the training data set we can use. So for this input, say, um, so one epoch means this is one iteration, right? So if I take this sample and put these values x1, x2, here number of n equal to 2, okay? So I need to just feed those values and select some initial W parameter, okay, including bias, okay? And um, that was my initial network parameter. And they will pass through the activation. So then immediately I will be able to know the output, okay? And then again activation, they will pass through the activation. Again I will know actual output, and I will see whether it is 0 or not. If it is not 0, then there will be error, and that I will propagate the error following this formula which we have discussed, and intuitively we will also try to see in my next class. So at least one complete epoch we will do by hand, so that you will be able to formulate thereafter the through programming the algorithm itself, right? So the difference between epoch and iteration, you know, this is one iteration, means I fed this and then see for run for each parameter, one data running rules has to be right. 1 plus delta W1. Okay, this needs to be calculated. So as many parameters are required, that many iterative loop you will have to compute. You see, that's why computationally this demands a lot of computation, isn't it? So many parameters, right? In a typical two input neuron, okay, you can see how many parameters will be there, right? And that exponentially it will increase if fully connected layer with large number of inputs are there. Okay. So this is one iteration. Then again, I will use this iteration, and this iteration, These will constitute one epoch. And then again I will go back next epoch. So that is the meaning of epoch, right? So W11 P plus 1 equal to W11 in a particular epoch P plus delta W in this particular epoch P. So in this way, I need to run the algorithm, right? Okay. So I think you have understood that why hidden layer weight correction require this term, because I need to reflect the influence of weight, which I have been able to figure it out here uh, for inputs of this J, so that I can compensate in turn this methodology, because they have contributed the error here. Okay, so I think it will be more clearly understood if I take this example in my next class. Till then, stay safe, have a nice day, goodbye.